So my intention is to speak for 21.5 plus or minus 0.5 minutes, starting from now. I want to at least entertain you to the point where I get one laugh, and I hope I'll give you some new ideas. I also want to, in the context of all the talks given today, provide a framework into which all of those will fit. So hopefully what I say will provide a framework in which you can understand that, but will be consistent with what everyone else says. So I've just done two things there. The first, I've provided you what in computing context will be called a unit test. I've said I'm going to do something, I've set a set of criteria, and at the end of the talk you will be able to judge, and I will be able to judge, whether I have in fact produced something that deals with those criteria and has therefore succeeded. What I won't do is the computing thing of then, if I don't succeed on my tests, of just redoing it and keep doing the talk until I in fact do. That will get a little bit dull after a while. The second thing I did was make a claim about the integration of what I'm going to say with everything else that's going on. So this is a thing that in the context of coding is called continuous integration, where whenever you generate some new code which uses other code or works within an existing framework, that you rebuild the whole thing and you check that everything works in the context of everything else. So these are two kinds of approaches in software engineering: unit testing, test-driven design, and continuous integration, that I want to use as kind of illustrative of good software practice. And I want to make a case for why good software practice is not just important in science for its own sake, but how it, thinking about science in that context, can help us to understand better ways of managing the scientific process, and indeed help us to imagine much better architectures for how we consider the way we do science more broadly. But let's go back to the first step. So why is good software coding important for science and for research more general? Well, the first is something that may seem trivial but is actually quite important, and Peter's already alluded to this, which is that a lot of what we get from the public funding of science is the creation of a trained workforce. And Peter's group systematically go out from the research setting and go into commercial software development settings where their skills are highly valued. So that's a non-trivial exercise in terms, particularly in terms of a situation where we're concerned in the training of graduate students in this country as less of a research project and more as a training exercise. That's actually a really important aspect of training people, not just for the small proportion who are going to end up in research, but the much larger proportion who are going to end up in other places, particularly where that's an important economic activity for the country that's funding that research. That's one aspect. But the more obvious aspect is that good code is good infrastructure for doing research. So when I want to rerun the fitting of the data I collected 6 months ago, that I'm actually able to do that. That I can find, firstly, where the software is to do the fitting, that I can find out and remind myself how to run it, and that I can test whether if someone's changed it, whether it's still doing what I'm expecting to do. This is just fundamentally good running of controls, good checking that software is in fact doing what it's said to be doing, and efficiently using my time, efficiently using the resources to make sure that the stuff that has been developed, the investment that has been made, is in fact useful. Because otherwise we spend a lot of time and a lot of money generating important resources that aren't actually used by anyone. I think it's also important at a bigger level, from the perspective of an experimental scientist. I often look at computational sciences and think that it looks like a much better world. That you run the computer and you don't have this problem of the experiment not working and the system breaking or the reagent not being there. And of course, and we know that's not true. I mean, I know many of you are computational scientists, and you know perfectly well that running the experiments often don't work, that things are often not in the right place. And yet at the same time, the very best of software practice, consistency testing, documentation, continuous integration, are things that actually speak to the values of science. A unit test is just a control in an experimental setting. I'm checking that the system, the experiment, the whatever I'm doing, when I do a simple test experiment where I know what the result should be, that's in fact what I get. Wouldn't it be great if we could actually do that automatically in our experimental science and across all of our computational science? In the context of continuous integration, we actually kind of do this. So we publish stuff. That gets tested in some highly inefficient way against the rest of the entire literature. And then eventually we go through this process of correction, cycling and republishing, and as long as you can get the funding to actually demonstrate that the other person was wrong, we eventually iterate towards a system that in fact describes the world reasonably well. And again, Brian has just shown you an example of how this could actually be tested in an automated way by linking the best of software systems that do this continuous integration, that do this testing, against the experimental data, and we can start to see how these things link together. So one of the really important things for me about high quality software engineering in the context of research is that actually it's one of the places where we can really push the agenda of high quality science, high quality experimental science, in a way that we can then expand into the experimental research world. And I think that's actually a really important thing, because to be blunt, the quality of our research and the way it is driven and the incentives which we operate under are pushing us in the opposite direction. We need to be serious about being able to replicate our experiments, and we're not. The impact factor of a journal is more closely correlated, is a better predictor of the chance of a paper being retracted than it is a predictor of the number of citations a paper will get.
Wow.
Just think about what that means in terms of the way we judge people, in terms of the incentives that are in place, in terms of who we fund and how we fund them. The papers that demonstrate that those big impact, really exciting papers were in fact a special case, a small example, don't get the attention, end up in other journals. And yet they're the important part, they're the actual real science. So my point is that this quality agenda is critical. Now the bottom line is, as I said, the incentives are not structured in the right way. So how do we change the incentives? How do we make things work so that high quality software design as part of the research process, that those skills of software engineering are a crucial and recognised and valued part of the research process, actually becomes integrated. So on the small scale, what we can do is we can just hack the system. We can take the existing set of metrics, the existing set of incentives, the existing set of measures, and just play with them a little bit. And this is what I and others have tried to do with a new journal being published hopefully very soon through BMC called Open Research Computation, in which we're creating a venue in which you can publish a paper, your conventional academic output, about a piece of software. So that's step one. We create a conventional output that can be put in a conventional CV, and you know, it's peer reviewed and all these things, you tick all these boxes, and so you've got conventional output. That's a start, but it's not an end, because this is a new journal that no one's heard of. So how do we actually make it a place where not just the people developing software for research would want to publish, but where the people who will be sitting on the panels judging whether to give that person a job will be concerned, will be understanding that this is a high quality piece of research output. And I say, we can hack the system here. So let's consider methods papers, software papers in particular. Now, some of those software papers describe software that gets used a lot. NWChem, Avogadro, software that sits underneath all sorts of things and is used over and over again, that is reusable. And the best software is the software that is well documented, that is well tested, that can be reused and is in an open source form that other researchers can build on it and use it on and refer to it. So if we can get enough papers into this journal, we don't need a very high proportion. Again, the impact factor is a really insane measure, but you can certainly play with it. So if we publish 100 papers a year, and 5 or 10 of those papers are these software packages that everyone uses that get 100, 200 citations a year, do the maths. Work out what the impact factor of the journal is. Yes, it's the wrong measure, but you can hack the system and you can play with it. So that's one route to saying that we value high-quality software engineering, of creating a place where people can say that they're doing it, and of providing a measure that other researchers would accept as a measure. Let me shift slightly to a different angle. So Peter's mentioned the Research Works Act, HR 3699, currently committee in the US Congress. So what this bill does is that it says that it is illegal for a US federal agency to require that published papers that result from their funded work be placed in an accessible repository. That's essentially what the Act would do. So it would actually stop PubMed working, for instance. It would wipe out the NIH mandate. It would certainly put open access back several years. The argument behind this Act is that publishers contribute intellectual property to the papers that they publish, and that they therefore have to have a right to receive recompense for that intellectual property. So I actually went through my last 10 papers, research papers, not the sort of commentary ones. And I went through line by line, word by word, figure by figure, to identify the intellectual property in the final submitted version, the version that had gone through peer review. And of those 10 papers, the total amount of intellectual property contributed by the publisher was 0. Not even a full stop. There were contributions from the peer reviewers, so the words, phrases, organisational issues that were contributed in that sense. But as a peer reviewer, I've never signed a contract that handed over the copyright in my peer review comments to the publisher. So the copyright in those, the intellectual property, those. So fine, so that's great. So what we do with the Research Works Act is just say there's no intellectual property, we don't need to pay the publishers at all. Well, that makes no sense either, because publishers do provide a service that is crucial to the process of publication. If you are going to have peer review, someone has to manage it. If we're going to put these papers into a form where they can be readily downloaded, someone has to do that work. If they're going to ensure that those go into indexes and go into the right places, then someone has to pay to have that done. Publishing is not a zero-cost game by any means. The problem is, and the reason why the Research Works Act is actually really insane for publishers to support, is that the historical reason why we transferred the IP to the publishers and then rented it back was because the costs of distribution, the costs of enabling access, were really quite high in a world where we had things printed on paper. Today, the cost of distribution is 0. The cost of providing access to a web page that exists on the web is 0. All the costs are tied up in the process of generating the first copy. So the publishers currently have a business model, a subscription-based model, have a business model where they are charging for things that cost nothing as a way of hiding the real costs of the process of publication. That's a really bad way to run a business. What we should be doing is having the discussion about how we transition from this business model to one where we create a market we have a transition period, where we talk about where those service costs should start, that we guarantee that we'll be able to pay them over a certain period of time, and that will have some transition costs, but that we support the creation of a market over some period of time for which these services are available. And that's the important thing, because if we continue to not pay for the bit of the publication process that costs money, then there's no guarantee that the services for which we want are going to continue to exist, because we're not paying for them. So it's not good for us, it's not good for the publishers, and there's a transitional problem. There's an issue of moving from here to there, and that's going to take time, and that's going to have a discussion. The problem with the Research Works Act is that it focuses on turning the clock back rather than saying we need to have a conversation about this and we need to talk about how we're going to do this globally. The point I want to make through that discussion is that we need to move to a concept of what services do we need, how do we build the market that support those services, how do we ensure that the diversity of services, the needs of the research community, the needs of the funders are supported, and that we have markets that support them, that include commercial players, that include not-for-profits, that include things that are placed within the funders themselves and within the research institutions. And my point is that actually we need to think, instead of thinking about this framework in which we purchase access, in which we purchase research, we need to turn the whole thing on its head and start thinking about this in terms of services. And so I bring this back to the issue of the software engineer in the research context. Part of the process of doing research is the service provided largely by institutions, increasingly by small software companies, because institutions are not able to provide this service, of software generation that is useful for the research community. It's a service. So we should stop talking about mandates, we should stop talking about IP, we should stop talking about the creation of even jobs at some level, and start saying, if as a country, if as a global, in a global context, we want to support research, we want to buy a service which is generating certain products, how do we configure the market, configure the service providers so that those can be provided? And what I don't mean is that we say, actually, I want the service of the creation of this particular piece of science. What I am saying is that the service level agreement between a funder and a research institution can include the expectations of what will be created and how it will be available and what the positions will be. And that the service level agreement between the research institution, their authors, and the publishers should also include the appropriate values. And that when we think about things from the perspective of how do we optimally create the outputs and the outcomes we want from research funding, what are the services we need, how do we create them, and how do we get from the world that isn't there to where that's possible, then we can start talking about a much more efficient, much more sensible system that's actually appropriate for the 21st century. And the place where we can start from the bottom up is by focusing on the quality of software engineering and the research we do. So I'll stop there.